On a clear winter night, high above the horizon, there is a star that glows with a faint reddish pulse. It sits on the shoulder of Orion, larger and softer than the surrounding points of light. To the naked eye, it seems almost close, almost reachable. But that red star is Betelgeuse, and it lies roughly 640 light-years away. 640 light-years, which means the light entering your eyes tonight began its journey before the invention of the telescope, before modern science, before most of the world as we know it even existed. So what would it really take to reach Betelgeuse? Not to look at it, not to simulate it, but to physically travel there. How long would the journey take with today's fastest spacecraft? What if we traveled at the speed of Voyager? What if we could move at 10% the speed of light? What if we somehow approached light speed itself? Would it take thousands of years? Millions? Or could advanced physics shorten the journey? And what would we even be traveling toward? Because Betelgeuse is not just a star. It is a red supergiant so enormous that if it replaced our Sun, it would swallow Mercury, Venus, Earth, and possibly Mars. Its surface boils and shifts. It dims and brightens unpredictably. And at any cosmic moment, it could explode in a supernova bright enough to outshine the moon. Traveling to Betelgeuse is not just a question of distance. It is a confrontation with scale, with time, with the limits of physics, and with the reality that the universe is far larger and far less accessible than our instincts suggest. Tonight, we are going to calculate the journey from chemical rockets to fusion engines to relativistic travel. We will measure the years, we will face the numbers, and we will discover what it truly means to attempt a voyage across 640 light-years of space. Because when you ask how long it would take to reach Betelgeuse, you are really asking how small we are and how far we still have to go. If we are going to understand how long it would take to reach Betelgeuse, we have to begin with something uncomfortable. Distance in space is not intuitive. On Earth, we measure journeys in kilometers, miles, hours, days. Even crossing oceans feels large to us. Flying from one side of the planet to the other feels extreme. But in cosmic terms, Earth itself is microscopic. Let's shrink things down. The distance from Earth to the Moon is about 384,000 kilometers. Light takes just over 1 second to travel that distance. The distance from Earth to the Sun is about 150 million kilometers. Light takes about 8 minutes to reach us. That already feels enormous. Now move outward. Jupiter, the giant of our solar system, sits about 5.2 astronomical units from the Sun. Light takes around 43 minutes to reach it. Neptune, the outermost major planet, is about 30 astronomical units away. Light takes over 4 hours to reach Neptune. 4 hours, and that is still inside our own solar system. Now take the next step. The nearest star to us, Proxima Centauri, is about 4.24 light-years away. That means light, the fastest thing in the universe, takes over 4 years to reach it. And Betelgeuse is approximately 640 light-years away. That means the light we see tonight left Betelgeuse around the year 1385, before the Renaissance, before modern astronomy, before the discovery of the Americas. If Betelgeuse exploded tomorrow, we would not know for centuries. That is the scale we are dealing with. But what does 640 light years actually mean in practical terms? 1 light year is the distance light travels in 1 year. Light moves at about 299,792 kilometers per second, roughly 300,000 kilometers per second. In 1 second, light could circle Earth more than 7 times. In 1 year, light travels about 9.46 trillion kilometers. Multiply that by 640. Betelgeuse is about 6 quadrillion, 54 trillion, 400 billion kilometers away. Over 6 quadrillion kilometers. The number is so large it stops meaning anything. So instead of kilometers, let's use something more human. Spacecraft speed. The fastest human-made object ever launched is NASA's Parker Solar Probe. At its peak speed near the Sun, it reaches about 192 kilometers per second. That sounds unbelievably fast. At that speed, you could travel from New York to Los Angeles in under 25 seconds. But space is not New York to Los Angeles. Let's do the math. At 192 kilometers per second, how long would it take to travel 6 quadrillion kilometers? If we maintained that maximum speed constantly, which we cannot, it would take roughly 1.05 million years to reach Betelgeuse. Over 1 million years. To put that into perspective, 1 million years ago, early humans had not yet evolved in the modern Homo sapiens. Civilization did not exist. Language as we know it did not exist. Agriculture did not exist. If we launched a spacecraft today at our maximum possible speed, it would arrive at Betelgeuse long after humanity itself may be extinct. And that is using our fastest object ever built. Now let's consider something even more sobering. Most spacecraft do not travel anywhere near 192 kilometers per second once they leave the Sun's gravity well. Voyager 1, currently the most distant human-made object, travels at about 17 kilometers per second relative to the Sun. At Voyager speed, the journey to Betelgeuse would take roughly 11 million years. 11 million years. For context, 11 million years ago, the human lineage had not even separated from early apes. Entire species have risen and vanished in less time. Civilizations are measured in thousands of years. Spacecraft to Betelgeuse at Voyager speed would require millions. So clearly, chemical rockets, the type that launched Apollo missions and modern probes, are insufficient. They are designed for planetary travel, not interstellar voyages. Chemical propulsion works by burning fuel and expelling exhaust at high speed. The problem is energy density. Chemical reactions simply do not release enough energy to accelerate massive spacecraft to significant fractions of the speed of light. To reach Betelgeuse within a human lifetime, we would need something radically different. Let's imagine we could travel at 1% the speed of light. That is about 3,000 kilometers per second, still far beyond current capabilities. But let's assume future propulsion systems could achieve it. At 1% light speed, the journey would take about 64,000 years, still longer than recorded human history. Now imagine 10% the speed of light. At 10% light speed, the journey would take 6,400 years. Better, but still longer than any civilization has ever lasted. Even if we could reach 50% the speed of light, half the fastest possible speed in the universe, it would still take 1,280 years. And here is where physics begins to matter in strange ways. At high fractions of the speed of light, Einstein's theory of relativity begins to dominate. Time dilation becomes significant. From the perspective of observers on Earth, the journey might take thousands of years. But from the perspective of travelers on board a near light-speed spacecraft, time would pass more slowly. If a ship traveled at 99% the speed of light, relativistic effects would dramatically shorten the subjective travel time for the crew. They might experience only a few decades while centuries pass on Earth. But reaching 99% light speed presents unimaginable engineering challenges. The energy required to accelerate even a modest spacecraft to that velocity would rival the total energy output of entire nations, or more. And deceleration would require just as much energy, because arriving at Betelgeuse at 99% light speed without slowing down would mean simply flying past it in a fraction of a second. Interstellar travel is not just about acceleration. It is about energy, fuel, shielding, navigation. Even tiny particles of dust become lethal at relativistic speeds. A grain of sand impacting a spacecraft at 50% light speed would release energy equivalent to a powerful explosion. The interstellar medium, though thin, is not empty. Now let's shift perspective again. Betelgeuse itself is not a stable destination. It is a red supergiant star nearing the end of its life. It is enormous, possibly over 700 times the radius of the Sun. Its outer layers are unstable. It dims unpredictably. In 2019 and 2020, Betelgeuse underwent a dramatic dimming event that sparked speculation about an imminent supernova. Eventually, whether in 10,000 years or 100,000, Betelgeuse will explode, and when it does, it will outshine the Moon in Earth's sky. If we launched a spacecraft today on a 6,400-year journey at 10% light speed, there is no guarantee Betelgeuse would even still exist in its current form upon arrival. We could be traveling toward a star that has already died. In fact, it is possible, though unlikely, that Betelgeuse has already exploded, and we simply have not seen it yet. That uncertainty adds another layer of cosmic scale to the question. Interstellar travel is not just about covering distance. It is about racing against stellar evolution. And that brings us to a deeper realization. The universe operates on timescales far beyond human lifetimes. Stars live for millions to billions of years. Galaxies evolve over hundreds of millions of years. Human civilization has existed for perhaps 10,000 years. We are measuring cosmic distances with species-level lifespans. And when we ask how long it would take to reach Betelgeuse, we are confronting that mismatch directly. At current technology levels, the answer is simple. We cannot reach Betelgeuse in any meaningful time frame. Not with chemical rockets, not with current propulsion, not with foreseeable near-term engineering. Even at optimistic future speeds, the journey would require thousands of years, which raises the next question. If we cannot reach it physically, could we ever truly explore it? Or is Betelgeuse destined to remain a distant beacon, studied through telescopes, mapped through spectroscopy, understood through physics, but never touched? In the next part, we will push further. We will explore theoretical propulsion systems, fusion drives, antimatter engines, light sails, and warp concepts. And we will see whether physics leaves even the slightest crack in the door for a journey across 640 light years. Because if reaching Betelgeuse seems impossible, that may simply mean we have not yet imagined the right way to try. If chemical rockets make the journey to Betelgeuse effectively impossible, then the only way forward is to imagine something far more powerful, to even begin talking about interstellar travel, especially to a star 640 light-years away. We must move beyond traditional propulsion entirely. The first step in that evolution would likely be nuclear propulsion, not nuclear bombs strapped to rockets, though that idea was seriously studied in the 1950s under Project Orion, but controlled nuclear reactions used to generate thrust far more efficiently than chemical fuel. Chemical rockets rely on rearranging electrons in atoms. Nuclear reactions rearrange nuclei themselves. The energy difference is enormous. A fusion reaction, for example, releases millions of times more energy per unit mass than chemical combustion. If we could build a functional fusion drive, something humanity is still struggling to achieve, even for electricity generation, spacecraft could potentially reach speeds of several percent of the speed of light. Let's imagine an optimistic scenario. Suppose we develop a fusion-powered spacecraft capable of reaching 5% the speed of light, that is 15,000 kilometers per second. At that speed, the journey to Betelgeuse would take around 12,800 years, still staggering. But now we are talking about a timescale that civilizations, not individuals, could potentially plan for. Yet even this optimistic speed presents enormous challenges. First, fuel. Fusion requires isotopes like deuterium and tritium, or perhaps helium-3. Storing and managing such fuel for thousands of years is an engineering challenge we cannot yet solve. Second, reliability. No machine humanity has ever built has lasted more than a few centuries at most. Even Voyager 1, our most enduring spacecraft, has been operating for just under 50 years. An interstellar fusion craft would need to function autonomously for millennia. Third, shielding. At 5% the speed of light, interstellar dust becomes dangerous. Even tiny particles would impact the spacecraft with tremendous kinetic energy. Over thousands of years, cumulative damage would be catastrophic unless protective systems were extraordinarily robust. So even fusion propulsion, while revolutionary compared to chemical rockets, barely scratches the surface of what is required. Now let's push further. What if we could harness antimatter? Antimatter annihilation is the most energy-dense reaction known to physics. When matter and antimatter meet, they convert directly into energy according to Einstein's equation. E equals squared. Even a small amount of antimatter could release immense energy. In theory, antimatter engines could accelerate spacecraft to 20%, 30%, even 50% of the speed of light. At 50% light speed, Betelgeuse could be reached in 1,280 years from Earth's perspective. But relativity changes the story. At 50% light speed, time dilation becomes noticeable, but not extreme. However, if we push closer to 90% or 99% of light speed, something extraordinary happens. From the perspective of the travelers on board, time slows dramatically relative to Earth. At 99%, the speed of light, time dilation would reduce the subjective travel time significantly. Earth might measure the journey as 640 years, but the crew might experience only a few decades. That changes everything. Suddenly, a human lifetime voyage becomes physically conceivable. But here is the brutal reality. To accelerate a modest spacecraft to 99% light speed would require energy comparable to the total output of humanity over centuries. And that is just acceleration. You would need the same energy again to slow down at the destination. Then there is the issue of antimatter production. We currently produce antimatter in particle accelerators, but in unimaginably small quantities. It is one of the rarest and most expensive substances ever created. Producing even a gram would require astronomical energy and cost. Containing it safely for centuries would require technologies far beyond current capability. Antimatter engines are not impossible according to physics, but they are staggeringly impractical with known technology. Now consider a different approach. Instead of carrying fuel, what if the spacecraft were pushed by light itself? This is the idea behind light sails. A large, ultra-thin reflective sail could be propelled by powerful lasers from Earth. The photons themselves, though massless, carry momentum. When they strike the sail, they transfer that momentum, gradually accelerating the spacecraft. Breakthrough Starshot, a real scientific initiative, proposes sending tiny gram-scale probes to Alpha Centauri at about 20% the speed of light using laser arrays. At 20% light speed, Betelgeuse could theoretically be reached in 3,200 years. But here is the limitation. Light sails are more realistic for very small probes, a tiny chip-sized spacecraft, not a human crew. Scaling the concept to a vessel capable of sustaining human life for centuries introduces enormous engineering complexity. Still, it demonstrates something important. Physics does not forbid high-speed travel. It simply demands extraordinary energy and engineering. Now, let's take one final step into speculation. Warp drives. The concept of a warp drive, inspired by science fiction, was given a theoretical foundation in 1994 by physicist Miguel Alcubierre. The Alcubierre drive proposes a way to bend space-time itself. Instead of moving a spacecraft through space faster than light, the drive would contract space in front of the craft and expand it behind, effectively allowing superluminal travel without locally exceeding light speed. In theory, this could allow travel across hundreds of light years in months, in theory. But there is a catch. Actually, several. First, the energy requirements are absurd. Early calculations suggested that creating such a warp bubble would require more energy than exists in the observable universe. Later refinements reduced that estimate, but it remains astronomically high. Second, exotic matter. Warp drives require negative energy density, a form of matter that may not even exist in usable quantities. Third, stability. Even if a warp bubble could be created, controlling it, steering it, and safely stopping it remain unsolved problems. At present, warp drives remain mathematical curiosities rather than engineering blueprints. So where does this leave us? Let's summarize the best realistic scenario. With advanced fusion propulsion, perhaps we could reach 5 to 10% light speed. That means 6,400 to 12,800 years of travel. With antimatter or highly advanced beam propulsion, maybe 20 to 50% light speed. That reduces the journey to 1,280 to 3,200 years. With extreme relativistic travel near 99% light speed, subjective travel time for the crew might be decades. But Earth would still age centuries. And Betelgeuse itself may evolve during that time. There is something deeply humbling in this. Betelgeuse feels close in the night sky. It is one of the brightest stars. It seems almost reachable, but in reality, it is separated from us by a gulf of time more than space. Even at our fastest conceivable speeds, we are dealing with thousands of years. Civilizations rise and fall in that time. Languages change, continents shift, and perhaps humanity itself transforms beyond recognition. So when we ask how long it would take to reach Betelgeuse, we are really asking something more profound. Are we a species capable of thinking in thousands of years? Are we willing to build projects whose completion we will never see? Are we prepared to launch journeys whose arrival lies beyond our lifetimes? Interstellar travel is not just an engineering challenge. It is a philosophical one. Because to reach Betelgeuse, we must first decide that the destination matters enough to justify centuries of effort. And even then, the star we arrive at may not be the star we left behind. In the next part, we will shift focus. Instead of propulsion, we will examine Betelgeuse itself. Because before committing to a 640 light-year journey, we must ask a simple question. What exactly are we traveling toward? And is Betelgeuse even a stable destination at all? Before we decide whether reaching Betelgeuse is worth thousands of years of effort, we need to understand what Betelgeuse actually is. Because Betelgeuse is not an ordinary star. It is not like our Sun. It is not even like most stars in the sky. Betelgeuse is a red supergiant, one of the largest and most unstable types of stars known. Located in the constellation Orion, Betelgeuse marks the hunter's shoulder. On a clear night, it glows with a deep orange-red color, distinctly different from the white-blue of many other stars. That color tells us something important. Betelgeuse is cool, at least by stellar standards. Its surface temperature is only about 3,500 Kelvin compared to the Sun's 5,800 Kelvin. But do not let that word cool mislead you. 3,500 degrees is still hot enough to melt steel instantly. The redness comes from its lower surface temperature compared to hotter blue stars. But temperature is not what makes Betelgeuse extraordinary. Size does. Betelgeuse is enormous. Estimates vary because measuring its exact size is difficult. Its outer atmosphere is diffuse and constantly shifting, but its radius is thought to be between 700 and 1,000 times that of the Sun. If Betelgeuse were placed at the center of our solar system, its outer layers would extend beyond the orbit of Mars. Some estimates even suggest it might approach the orbit of Jupiter during certain expansion phases. Imagine that. the Sun replaced by a star so large that Earth, Mercury, and Venus would all be inside it. And yet, despite its size, Betelgeuse is not particularly massive compared to some other stars. Its mass is estimated to be around 10 to 20 times the mass of the Sun. That means it is much less dense than the Sun. It is like a colossal cosmic balloon, huge in volume, but relatively sparse in density. That bloated structure tells us something critical. Betelgeuse is dying. Red supergiants are stars in the late stages of stellar evolution. They have exhausted the hydrogen fuel in their cores and have begun fusing heavier elements. The process is violent and unstable. The star expands dramatically. Its outer layers become turbulent. Convective cells, unimaginably large, rise and fall across its surface. On the Sun, convection cells are about the size of Texas. On Betelgeuse, a single convection cell could be as large as Earth's entire orbit. Its surface is not smooth or stable. It boils, it pulses, it sheds material into space. Betelgeuse is losing mass at an extraordinary rate, ejecting gas and dust that form a vast circumstellar envelope around it. In 2019, something remarkable happened. Betelgeuse dimmed dramatically. Its brightness dropped by nearly 60%, a phenomenon that became known as the Great Dimming. For months, astronomers watched as the star faded. Speculation exploded. Was this the beginning of its supernova? Was Betelgeuse about to die in a cosmic explosion, visible even in daylight from Earth? Eventually, detailed observations revealed that the dimming was likely caused by a massive dust cloud expelled from the star's surface, partially obscuring it. But the event was a stark reminder. Betelgeuse is unstable. Its death is inevitable. The only uncertainty is timing. It could explode tomorrow. It could explode in 10,000 years. It could explode in 100,000 years. In cosmic terms, that is soon. So now, we must confront a profound reality. If we launched a spacecraft toward Betelgeuse at 10% the speed of light, requiring 6,400 years, there is a real possibility that the star would explode before we arrived. Even worse, it may have already exploded, because the light we see from Betelgeuse left it 640 years ago. If it exploded in the year 1500, we would not know yet. We are always looking into the past. Reaching Betelgeuse physically means traveling not just across distance, but toward a moving target in time. Now consider what happens when Betelgeuse dies. It will not simply fade away. It will undergo a core collapse supernova. When the core runs out of fuel, it will no longer be able to resist gravitational collapse. The core will implode in milliseconds. Temperatures will soar into the billions of degrees. A shock wave will blast outward, tearing the star apart. For weeks or months, Betelgeuse will outshine entire galaxies. From Earth, it may appear as bright as the full moon. After the explosion, what remains? Possibly a neutron star, perhaps even a black hole, depending on its final mass. The star we see now, that vast, glowing red supergiant, will be gone, replaced by a compact remnant. So what exactly are we traveling to? A dying star. A star shedding its outer layers. A star on the brink of catastrophic collapse. Betelgeuse is not a stable destination like a main sequence star. It is a ticking clock. And that introduces another complication: radiation. Red supergiants emit enormous stellar winds. If we approach Betelgeuse, we would encounter a hostile environment filled with high-energy particles and dense clouds of gas and dust. As it nears supernova, that environment would grow even more extreme. Any spacecraft traveling toward it would need shielding far beyond anything currently conceived. And if we arrived during or shortly after its explosion, the radiation levels would be lethal across vast distances. In fact, if Betelgeuse were only 50 light-years away, its supernova could potentially damage Earth's biosphere. At 640 light-years, we are safe, but close to the star itself. The explosion would sterilize anything nearby, so perhaps the goal would not be to approach closely. Perhaps we would aim to orbit at a safe distance, study it, observe its death firsthand. But even that introduces staggering technical challenges. A supernova is not a slow event. The core collapse happens in seconds. The shockwave travels outward at thousands of kilometers per second. To witness it from close range, we would need to arrive at precisely the right moment. Too early, and we wait for centuries. Too late, and we miss the most violent phase. Betelgeuse forces us to confront something uncomfortable about interstellar travel. Stars evolve on their own timelines. We cannot command them to wait for us. And here is another complication. Betelgeuse's size fluctuates. Recent observations suggest that it may have shrunk slightly over the past decades. Or perhaps we are simply measuring different layers of its atmosphere. Its outer envelope is not a solid surface. It is diffuse and dynamic. If we imagine landing on Betelgeuse, we quickly realize there is nowhere to land. Red supergiants do not have solid surfaces. Their outer layers are tenuous gas. A spacecraft descending toward Betelgeuse would encounter increasing density and temperature until it was vaporized. There is no ground, no stable orbit close to the star, no planetary system known to exist around it. Betelgeuse is not a destination in the sense we understand. It is an event in progress. So why do we even consider traveling there? Because Betelgeuse represents a rare opportunity. It is one of the closest stars likely to undergo a supernova, in astronomical soon. Studying it up close would revolutionize our understanding of stellar death. Supernovae are responsible for creating heavy elements: carbon, oxygen, iron. The atoms in your blood were forged in stars like Betelgeuse. Observing such an event firsthand would answer questions about element formation, neutron star creation, black hole thresholds, and galactic evolution. But here is the final irony. Even if we never reach Betelgeuse physically, we may not need to. Modern telescopes already resolve details on its surface. Interferometry allows us to see convective cells. Spectroscopy reveals its composition. Radio and infrared imaging map the dust it ejects. And future observatories, both on Earth and in space, will provide even greater clarity. We are learning about Betelgeuse without leaving home. Perhaps interstellar travel is not required to understand distant stars. Perhaps the journey is symbolic rather than practical. Because when we ask how long it would take to reach Betelgeuse, we are really asking, can humanity ever bridge the gap between curiosity and capability? Betelgeuse is not just far away. It is unstable. It is evolving. It is dying. And by the time we could reach it, if we ever could, it may already be something entirely different. In the next part, we will turn from the star itself to the travelers, because if we are to imagine a 6,000-year or 600-year journey, we must ask, who would make that trip? And what kind of civilization would they represent? If reaching Betelgeuse requires thousands of years, then the most important question is no longer about propulsion. It is about people. Because interstellar travel on that scale is not a mission. It is a civilization. If the journey takes 6,400 years at 10% the speed of light, no single human could survive it. Even with life extension technologies, the biological limits of the human body make millennia-long lifespans implausible with known science. So who arrives? Not the ones who launched, but their descendants. This changes the nature of the mission completely. A voyage to Betelgeuse at sublight speed would almost certainly require a generation ship, a self-sustaining spacecraft designed not just for travel, but for life, an artificial world drifting between stars. Imagine a vessel kilometers long, rotating to simulate gravity through centrifugal force, containing ecosystems, water cycles, agriculture, and closed-loop life support systems. A miniature biosphere traveling through interstellar darkness. It would not simply be a spacecraft, it would be a moving planet. And that introduces challenges far more complex than propulsion. First, sustainability. Every ecosystem on Earth relies on vast planetary cycles, oceans, atmosphere, tectonics, sunlight, microbial diversity. Recreating even a tiny fraction of that stability inside a spacecraft is staggeringly difficult. We have attempted closed ecosystems before. In the early 1990s, Biosphere 2 attempted to simulate a sealed environment for just a few years. It struggled. Oxygen levels fluctuated. Species died off. Unexpected chemical reactions destabilized the system. Now imagine maintaining ecological stability for thousands of years. Every imbalance would compound. Every species loss would ripple through the system. The margin for error approaches zero. Second, governance. A generation ship would contain thousands, perhaps millions, of people over centuries. Societies change, beliefs shift, political systems evolve. After 100 generations, would the inhabitants even remember why they were traveling? Would the mission still matter? Or would Betelgeuse become a myth, a distant legend about a star their ancestors once aimed for? Human history shows that even nations lasting a few centuries undergo radical transformations. A starship civilization lasting thousands of years would evolve in unpredictable ways. Language might change. Culture would certainly change. The meaning of Earth might fade. Third, psychology. Living inside a closed structure, knowing you will never see the destination, only your distant descendants might, requires extraordinary psychological resilience. The sky would never change. There would be no sunrise beyond the artificial light cycle, no stars growing brighter as you approach. For most of the journey, Betelgeuse would remain a faint red point, barely different from how it appears from Earth. The sense of motion would be abstract. Humans evolved on open plains under vast skies. Could we adapt to living in a rotating cylinder of metal and glass for millennia? Then comes another possibility. Instead of sending living humans, what if we send embryos, frozen genetic material, or artificial womb systems? The spacecraft could travel autonomously for thousands of years and begin human colonization upon arrival. In this scenario, the crew does not exist during most of the journey. They are born near the destination. This eliminates the generational burden, but it introduces ethical questions. Who raises the first generation? Artificial intelligence? Robotic caretakers? What cultural foundation would they inherit? They would be children born without Earth, their entire understanding of humanity constructed from archived data. They would not be travelers. They would be settlers created by a distant, ancient civilization. And that raises a deeper question. Would they still consider themselves human? Now consider an even more radical approach: digital consciousness. If future technology allows the human mind to be scanned and uploaded into digital systems, then perhaps travelers would not be biological at all. Instead of sustaining bodies for thousands of years, we sustain data. A ship containing digital minds could operate with far lower life support requirements. Time would become flexible. Digital consciousness might experience centuries in seconds, or slow perception down to match interstellar travel times. The journey to Betelgeuse might not feel long at all. But again, this depends on technologies we do not yet possess. Even if possible, the philosophical implications are immense. Would a digital copy of a human mind still be the same person, or merely a replica? And what happens if the system fails after 5,000 years? Redundancy would be essential. Multiple backups, multiple ships, because interstellar space is not empty. It contains radiation, micrometeoroids, cosmic rays. Over thousands of years, even small risks accumulate. Now let's confront something uncomfortable. Even if we solve propulsion, sustainability, governance, and psychology, there is still the matter of purpose. Why Betelgeuse? It has no known habitable planets. It is nearing supernova. It is not a stable, long-term destination for colonization. So perhaps the mission would not be to settle, but to observe, to witness a star's death up close. But does that justify thousands of years of travel? We must compare it to alternative uses of that energy. The energy required to accelerate a spacecraft to 10% light speed could transform entire planetary civilizations, terraform Mars, build orbital habitats, construct Dyson-like energy collectors around our own sun. In other words, the cost of reaching Betelgeuse may exceed the value of what we gain, which brings us to another possibility. Maybe we never physically go. Maybe we send probes, tiny durable machines capable of traveling at relativistic speeds. Artificial intelligence does not require oxygen. It does not suffer boredom. It does not question purpose. A fleet of microprobes propelled by powerful lasers could reach Betelgeuse in a few thousand years, perhaps even less. If speeds approach 20% light speed, they could transmit data back to Earth via laser communication. But even then, communication delay is 640 years one way. Any message sent from Betelgeuse would arrive more than 6 centuries later. The explorers would be long gone before Earth hears their findings. Interstellar travel fractures causality in practical terms. Exploration becomes asynchronous. You cannot react in real time. You cannot adjust plans based on immediate feedback. Everything operates on century-long delays. And this reveals something profound. The universe is not built for fast travel between stars. It is structured around immense separations. Perhaps that is not an accident. Perhaps interstellar distances serve as a natural boundary, encouraging civilizations to focus inward before expanding outward. Now consider another angle. If Betelgeuse were to explode while a generation ship was en route, what then? The travelers might arrive to find a neutron star and an expanding supernova remnant. the star they aimed for would be gone. Would they continue past it, turn back, or settle near the remnant? The mission's meaning would shift instantly. This uncertainty forces us to confront the deepest reality of a Betelgeuse journey. It is not just about reaching a star. It is about committing to uncertainty across millennia. And that is something humanity has never attempted. We build monuments lasting centuries. We plan projects spanning decades, but thousands of years. That requires a mindset closer to geology than politics, closer to stellar evolution than economics. So perhaps the most realistic answer to who would make the trip is not us, not our children, not even our grandchildren. It would require a civilization that sees itself as a continuous entity across millennia. A civilization stable enough to maintain purpose for thousands of years. A civilization willing to invest in a future it will never personally witness. In the next part, we will explore something even stranger. Because if human lifetimes are too short and generational ships too fragile, perhaps the only way to reach Betelgeuse is to change what it means to be human altogether. If the journey to Betelgeuse demands more than faster engines and stronger ships, then perhaps the true limitation is not physics. Perhaps it is biology. Because when we talk about traveling 640 light years, we are really talking about pushing beyond what the human body was ever meant to endure. Humans evolved under one star, on one planet, within one thin atmosphere. Our biology is optimized for gravity of 1G, radiation filtered by Earth's magnetosphere, and lifespans that rarely exceed a century. Interstellar space offers none of that. It is cold, it is irradiated, it is empty, and it is unimaginably long. So what if the only way to reach Betelgeuse is not by building better ships, but by redesigning ourselves? The first frontier would be longevity. If we could extend human lifespan from 100 years to 1,000 years, the equation changes immediately. At 10% light speed, a 6,400-year journey becomes 6 or 7 lifetimes instead of 64. With radical biological modification, perhaps even longer lifespans are conceivable. Gene editing, cellular regeneration, nanotechnology repairing tissue at the molecular level. These are not pure science fiction. Early forms already exist in laboratories, but extending life indefinitely presents deep biological challenges. Cells accumulate mutations, proteins degrade, telomeres shorten, neural pathways deteriorate. We would need to fundamentally re-engineer the maintenance systems of life itself. And then comes radiation. Interstellar space is filled with high-energy cosmic rays. Even inside a heavily shielded spacecraft, long-term radiation exposure would damage DNA. Cancer risk would skyrocket. Neurological damage would accumulate. So perhaps we engineer radiation-resistant humans, some microorganisms on Earth, like Deinococcus radiodurans, can survive extreme radiation levels. Could we incorporate similar repair mechanisms into human DNA? Could we design future humans to tolerate cosmic environments the way we tolerate sunlight? And what about gravity? A multi-thousand-year journey likely involves long periods of microgravity or artificial gravity from rotating habitats. Human bodies degrade quickly without gravity. Bone density decreases, muscle mass declines, cardiovascular systems weaken. We would need either permanent artificial gravity or humans redesigned for lower gravity conditions, shorter limbs, stronger connective tissues, different skeletal structures. Over thousands of years aboard a generation ship, natural selection might reshape humanity anyway. Those best adapted to the ship environment would thrive. A new branch of humanity could emerge before arrival. The Betelgeuse settlers might not resemble us at all. Now imagine a more radical shift. Instead of modifying biology gradually, what if we abandon it entirely? Cybernetic augmentation. Brain-computer interfaces already allow limited interaction between human neurons and machines. Future versions could allow memory expansion, sensory extension, even partial digital integration. Over centuries, humans might become hybrids, biological cores sustained by mechanical bodies. Mechanical bodies capable of self-repair, radiation resistance, and extreme longevity. A cybernetic traveler might endure thousands of years far more easily than a purely biological one. And if we push this further, complete digital transfer of consciousness, the journey becomes something entirely different. Instead of carrying fragile bodies, we transmit minds, encoded, compressed, stored. A spacecraft carrying servers rather than living tissue. Time dilation would matter less. Power supply becomes the primary concern. Radiation shielding becomes simpler for electronics than for living organisms. But then comes the question that philosophers have wrestled with for centuries. If you upload your mind into a machine, is it still you? Or is it merely a copy? Would the digital entity feel continuity of consciousness? Or would it simply believe it does? And does the distinction matter if the journey spans thousands of years? Perhaps by the time Betelgeuse is reachable, humanity will no longer define itself by flesh. The travelers may be post-biological intelligences, entities capable of slowing their perception of time so that 6,000 years feels like a week. Entities capable of entering dormant states for centuries. Entities that can replicate themselves, repair themselves, adapt dynamically. In that scenario, interstellar travel becomes less about survival and more about persistence. But even then, there are limits. Energy remains fundamental. Accelerating any mass, biological or digital, to relativistic speeds requires immense power, and decelerating safely requires the same. Then there is communication. If Betelgeuse explorers discover something extraordinary, their message will take 640 years to reach Earth. If Earth responds, another 640 years pass before the reply arrives. Civilizations change dramatically in that time. The conversation becomes one between distant epochs rather than contemporaries. This leads to a startling possibility. By the time a ship reaches Betelgeuse, Earth itself may no longer exist in recognizable form. Climate shifts, technological revolutions, artificial intelligence singularities, even extinction events. The travelers may be the last remnant of an ancient Earth civilization long forgotten, or they may arrive only to discover that Earth advanced far beyond them, perhaps developing faster than light communication or abandoning physical travel entirely. Interstellar missions risk becoming isolated time capsules, frozen cultural artifacts drifting through cosmic darkness. And then there is Betelgeuse itself. If it explodes during the journey, the travelers may approach a supernova remnant instead of a red supergiant. The destination would transform. A a neutron star spinning rapidly, a pulsar emitting beams of radiation, or perhaps a newly formed black hole? Would the mission continue? Or would it shift focus to studying the aftermath? Perhaps that is the true goal, witnessing stellar death up close. Supernovae create heavy elements. The calcium in your bones, the iron in your blood, all forged in ancient stellar explosions. Studying one from nearby would unlock secrets of cosmic chemistry. But here is the paradox. We already study supernovae from Earth. Advanced telescopes observe distant explosions across the universe. Neutrino detectors capture signals from stellar collapses. Gravitational wave observatories detect mergers of neutron stars. We gain knowledge without risking thousands of years of travel. So what justifies going? Perhaps it is not science alone. Perhaps it is something deeper. Exploration is woven into human psychology. From crossing oceans to climbing mountains, we move outward not only for survival, but for meaning. Betelgeuse is a symbol, a beacon, a reminder that the universe is vast beyond comprehension. To reach it would be to declare that distance itself is not an absolute barrier, but the cost in energy, time, and transformation would reshape humanity completely. We would no longer be a planetary species. We would become a multi-generational, possibly post-biological civilization thinking in millennia. And perhaps that is a true journey, not from Earth to Betelgeuse, but from biological humanity to something far more enduring. In the next part, we will confront an uncomfortable truth. Because even if we could redesign ourselves, build generation ships, harness fusion or antimatter, there may still be one final barrier. Not technological, not biological, but physical. The structure of space-time itself. Even if we solve propulsion, even if we redesign the human body, even if we build generation ships that can survive thousands of years, there is still one final boundary that cannot be engineered away so easily: the speed of light. According to everything we currently understand about physics, the speed of light is not just a suggestion. It is a limit, a fundamental property of space-time. Nothing with mass can reach it. Nothing with mass can exceed it. And this is not simply a technological limitation. It is woven into the structure of reality itself. Einstein's theory of special relativity tells us that as an object with mass accelerates closer to the speed of light, its relativistic mass increases. The faster it goes, the more energy is required to push it even faster. As it approaches light speed, the energy requirement approaches infinity. Infinite energy, not large, not extreme, infinite. This means that no matter how advanced our engines become, fusion, antimatter, beam propulsion, reaching exactly 100% light speed is physically impossible for anything with mass. And Betelgeuse is 640 light-years away, which means even traveling at light speed would take 640 years from Earth's frame of reference. But we cannot even do that. This is where relativity begins to feel like a wall. However, relativity also introduces something strange: time dilation. If a spacecraft travels at 99.9% the speed of light, time on board slows dramatically relative to Earth. From Earth's perspective, the journey might take 640 years, but on board the ship, the travelers might experience only a few decades. Push closer, 99.99%, 99.999%. and the subjective time shrinks further. In theory, the crew could reach Betelgeuse within their lifetimes, while centuries pass on Earth. But this introduces a haunting consequence. When they arrive, Earth will not be the Earth they left. Civilizations may have collapsed. Humanity may have evolved or vanished. Relativistic travel is not just spatial displacement. It is temporal displacement. You arrive in the future, one way. There is no return to your original time. Now let's examine the energy required to accelerate even a modest spacecraft, say 1,000 tons, to 99% light speed, would require energy on the order of 10 to the power of 19 joules. That is comparable to the total energy output of humanity over many years. And again, you need the same amount to slow down at Betelgeuse, and the same to return. Interstellar travel at relativistic speeds is not just a matter of building a better engine. It is about harnessing energy on a planetary or even stellar scale. This leads to the concept of Kardashev civilizations. A Type 1 civilization harnesses the energy of its planet. A Type 2 civilization harnesses the energy of its star. A Type 3 civilization harnesses the energy of its galaxy. Humanity is currently around Type 0.7. To send relativistic missions regularly, we would likely need to approach Type 2 status. That means constructing massive solar collectors, perhaps Dyson swarms, around our Sun, collecting a significant fraction of its 3.8 times 10 to the 26th power watts of output. Only then would the energy requirements for near light speed travel become practical. But even if we solve energy, even if we master relativistic engineering, there remains another danger. Interstellar space is not perfectly empty. At relativistic speeds, even a single hydrogen atom becomes dangerous. At 99% light speed, the kinetic energy of tiny dust grains becomes enormous. Collisions would release explosive amounts of energy. A spacecraft would need a shielding system capable of absorbing constant high-energy impacts for years. Some proposals suggest forward-facing magnetic fields to deflect charged particles. Others propose sacrificial shielding layers. But the faster you travel, the greater the hazard. There is a trade-off between speed and survivability. Now consider communication again. Even at light speed, messages take 640 years to reach Betelgeuse, which means no real-time updates, no remote control, no rescue missions. The spacecraft must be completely autonomous. And autonomy over centuries introduces unpredictable variables. AEI systems must function without corruption. Power systems must endure. Mechanical parts must resist degradation. Over thousands of years, entropy always wins, unless maintenance systems are flawless. Then there is gravitational navigation. Stars move. Betelgeuse is not stationary relative to Earth. Over thousands of years, its position shifts. A spacecraft must account for stellar motion across millennia. Navigation becomes a problem not just of direction, but of predicting galactic dynamics far into the future. Even tiny miscalculations could lead to missing the target by astronomical distances. Now let's address the elephant in the room: faster than light travel. Science fiction has normalized the idea. Warp drives, wormholes, hyperspace. But current physics offers no practical method for exceeding light speed. Wormholes, theoretical tunnels connecting distant regions of spacetime, may exist mathematically, but maintaining one would require exotic matter with negative energy density. We have observed small quantum effects that produce negative energy in tiny amounts, such as the Casimir effect. But nothing remotely scalable. Warp drives, like the Alcubierre metric, theoretically allow space itself to move faster than light while the ship remains locally stationary. But again, enormous energy requirements, exotic matter, instability issues, and no experimental evidence that such systems are physically realizable. So we are left with a stark conclusion. The universe enforces separation. Stars are distant for a reason. The speed of light acts like a cosmic speed governor. It prevents rapid expansion. It forces civilizations to think long-term, or not at all. But perhaps that is not a limitation. Perhaps it is a filter. Civilizations that cannot cooperate across centuries, the stability required for millennia-long missions. Betelgeuse may not just be far. It may represent a threshold of maturity. To reach it, we would need energy at stellar scales, engineering at planetary scales, biology redesigned for cosmic endurance, society stable across millennia, and patience beyond anything humanity has ever demonstrated. Now imagine we succeed. A relativistic ship departs Earth. Centuries pass on Earth. Decades pass on board. The crew arrives. Betelgeuse looms enormous and red, filling the sky. Perhaps it has not exploded yet. Perhaps they witness its final years. Perhaps they see the core collapse unfold in real time. For them, it would be a triumph of civilization. For Earth, it would be ancient history. Because by the time their data returns, 1,280 years will have passed, 640 out, 640 back. And Earth may no longer exist in recognizable form. Interstellar travel fractures continuity. It divides cause and effect across centuries. It transforms explorers into temporal exiles. And this is the final barrier. Not just speed, not just energy, but time itself. To reach Betelgeuse is to accept that you are leaving not only your planet, but your era. In the next part, we will confront a deeper question. Because perhaps the greatest obstacle to reaching Betelgeuse is not physics. It is whether humanity truly wants to cross a gulf that may never be bridged in our own lifetime. Before we ask whether humanity can reach Betelgeuse, we have to ask something even more uncomfortable. Would we actually choose to? Because a 640 light-year journey is not just a technological undertaking. It is a decision about identity. Every major leap in human history, crossing oceans, building cities, splitting the atom, was driven by necessity, ambition, fear, curiosity, or survival. But Betelgeuse offers none of those in any immediate sense. It is not habitable. It is not resource-rich. It is not a strategic location. It is not even stable. It is a dying star. So why go? To answer that, we have to examine the psychology of exploration itself. Humans are not purely rational explorers. We crossed the Pacific before understanding what lay beyond it. We climbed Everest long before it served any practical purpose. We walked on the moon knowing it would not solve Earth's problems. Exploration is not always about utility. It is about meaning. Betelgeuse is one of the brightest stars in the sky. It is visible to the naked eye. It glows red in Orion's shoulder. Ancient civilizations noticed it, named it, built myths around it. It has been a symbol for thousands of years. But now we understand what it truly is. a red supergiant nearing catastrophic collapse. It will explode, not metaphorically, literally. When it does, it will briefly rival the brightness of the moon. It will become a cosmic spectacle visible even in daylight. That inevitability creates something powerful. Betelgeuse is not just a star. It is a future event, and humanity has always been drawn to events. The idea of witnessing a supernova up close, of watching a star die in real time, is one of the most dramatic scientific opportunities imaginable. But here is the tension. By the time we could physically reach Betelgeuse, it may have already exploded, or it may still have thousands of years left. We cannot schedule stellar death. The universe does not coordinate with our timelines, which means any mission to Betelgeuse is fundamentally uncertain. You are not traveling to a fixed monument. You are traveling toward a ticking clock. Now imagine the political side. To launch a Betelgeuse mission would require a planetary-scale consensus, resources equivalent to decades of global energy output, infrastructure spanning continents, commitment across generations. Would humanity cooperate long enough? History suggests instability is our default state. Empires rise and fall within centuries. Technologies disrupt societies in decades. Climate systems shift over centuries. Interstellar travel requires stability at a scale we have never demonstrated. It demands that humanity think not in election cycles, but in millennia. That is unprecedented. And yet, there is another possibility. Perhaps Betelgeuse is not the goal. Perhaps it is the proving ground. To design propulsion capable of reaching Betelgeuse means we can reach closer stars far more easily. If we can travel 640 light-years, then Proxima Centauri at 4.24 light-years becomes trivial. Even a journey at 10% light speed would reach Proxima in 42 years. That is within a human lifetime. In that sense, Betelgeuse represents the extreme case, the edge of our ambition. If we can reach that far, then the galaxy opens. But here is something else to consider. The Milky Way is about 100,000 light-years across. Even if we mastered 10% light speed travel, crossing the galaxy would take 1 million years. Even at near light speed, the galaxy remains enormous. Betelgeuse is not even that far in galactic terms. It is just 640 light-years away, a tiny fraction of the Milky Way's diameter, and yet it feels unreachable. This tells us something profound. The galaxy is not built for rapid traversal. It is built for patience. Now let's confront another layer. What if humanity does not remain biological? What if artificial intelligence surpasses us within centuries? What if machine civilizations inherit our technology? A machine intelligence may not be constrained by lifespan or psychology. It may think in thousands of years effortlessly. It may value long-term missions in ways we struggle to. For such a civilization, Betelgeuse is not impossibly far. It is simply distant. A 6,000-year journey is not emotionally heavy if you are not biologically mortal. An AI civilization powered by solar energy collectors could launch relativistic probes without hesitation. They would not fear boredom. They would not fear generational drift. They would not fear missing Earth. To them, interstellar exploration could be routine. And this raises a haunting thought. Perhaps advanced civilizations elsewhere in the galaxy already do this. Perhaps the reason we see no alien visitors is not because they cannot travel, but because the distances are so vast that encounters are rare and asynchronous. A civilization 640 light-years away might send probes that arrive thousands of years after its own extinction. The galaxy could be filled with ancient machines drifting between stars, silent, patient, unhurried. Betelgeuse may already have visitors. We simply would not know. Now imagine the reverse. If humanity develops relativistic travel, we may send probes to hundreds of stars simultaneously, not to colonize, but to observe, to see data archives, to leave markers of existence. Interstellar travel becomes less about migration and more about persistence, about ensuring that even if Earth fades, humanity's knowledge survives elsewhere. Betelgeuse could be one node in a vast network of interstellar archives. But again, this assumes long-term stability, and stability is rare in intelligent species. Which brings us back to the core question: would we actually choose to reach Betelgeuse? If Earth faces existential threats, climate collapse, asteroid impacts, technological self-destruction, resources might shift towards survival rather than exploration. Interstellar travel could seem like luxury. On the other hand, existential threats might accelerate it. If Earth becomes unstable, spreading beyond the solar system becomes insurance. But Betelgeuse is not a safe refuge. It is dying. So perhaps the true value lies not in settlement, but in understanding. Understanding stellar evolution, understanding supernova physics, understanding how heavy elements form. Because every atom in our bodies was forged in ancient stars. Betelgeuse represents our origin story in progress. Watching it die is like witnessing the future of all massive stars, including the ancestors of our own sun. So maybe the journey is symbolic, a pilgrimage to a cosmic ancestor, not to live there, but to learn, to bear witness, to prove that intelligent life can cross 640 light-years of space through cooperation and patience. Yet there remains the hardest truth of all. Even if we commit, even if we build, even if we launch, the journey will outlast us. And that is something humanity has never done willingly. We build for centuries, but thousands of years. It requires faith, faith in descendants we will never meet, faith in institutions we cannot control, faith that meaning will persist. Betelgeuse forces us to confront that faith. It asks whether humanity is a short-lived flare in cosmic history, or the beginning of something far more enduring. In the next part, we will explore a different angle, because perhaps the real answer to reaching Betelgeuse is not to travel physically at all. Perhaps the only way to truly reach it is to change how we define presence itself. There is another way to think about reaching Betelgeuse, not with engines, not with generation ships, not with bodies at all, but with information. Because in the modern era, we have already begun to extend ourselves across space without physically traveling there. When we look at Betelgeuse through telescopes, we are not merely observing light. We are decoding information. Spectral lines reveal chemical composition. Brightness variations reveal surface convection. Infrared emissions reveal dust clouds. Radio waves reveal mass loss. We are not at Betelgeuse, but we are extracting its secrets. And that raises a provocative idea. Perhaps reaching a star does not require touching it. Perhaps it requires understanding it so completely that distance becomes irrelevant. Consider how much we have already achieved from Earth. Interferometric arrays can resolve surface features on Betelgeuse. Space telescopes can measure its size changes. Neutrino detectors can capture particles from distant stellar events. We are observing stars in other galaxies without leaving orbit. In a sense, our instruments are our extensions. They are our senses stretched across space. Now imagine future telescopes, kilometer-wide interferometers in space, swarm arrays orbiting the Sun, gravitational lens telescopes using the Sun itself as a focusing lens. The solar gravitational lens begins to focus light from distant objects at about 550 astronomical units from the Sun. If we place a telescope at that distance, far beyond Pluto, we could achieve imaging resolutions unimaginable today. We might see exoplanet surfaces. We might observe Betelgeuse's convective cells in extraordinary detail. We might map its atmosphere layer by layer, all without traveling 640 light years. In that scenario, the journey to Betelgeuse becomes a journey within our own solar system, a mission of hundreds of astronomical units rather than trillions of kilometers. Still challenging, but manageable within centuries rather than millennia. And then there is artificial intelligence. Future AI systems could analyze astronomical data at scales no human mind can comprehend. They could simulate Betelgeuse's interior in extreme detail, predict its supernova timeline more precisely, model the exact dynamics of its core collapse. Through simulation and observation combined, we could understand Betelgeuse almost as if we were there. And this introduces something subtle. Presence does not always require proximity. If you can observe, measure, simulate, and predict a system with extraordinary accuracy, you have, in a meaningful sense, reached it. But there is still a difference. There is something profound about physical presence. When humans walked on the moon, they did not gain knowledge that robotic probes could not gather. They gained something symbolic, a confirmation that we could physically cross the void. So perhaps reaching Betelgeuse physically is not about science. It is about proving that distance is not absolute. Yet we must acknowledge a deeper constraint. Even if we could transmit ourselves as pure data, encoded consciousness sent at near light speed, the signal would still take 640 years to arrive. We cannot escape light speed delay unless we discover new physics. Quantum entanglement is often mentioned as a potential loophole, but entanglement does not allow faster than light communication. It correlates particles instantaneously, but information transfer remains bound by relativity. The universe guards causality fiercely. So if presence through information is limited by light speed, perhaps we redefine the goal again. Instead of sending ourselves, we send probes equipped with advanced fabrication systems, machines capable of constructing observatories upon arrival, self-replicating systems, von Neumann probes. These theoretical machines could harvest local materials and replicate themselves. A single probe sent toward Betelgeuse could, over centuries, create an entire observational infrastructure there, and once established, it could transmit back continuous streams of data. The first message would take 640 years to arrive, but after that, a steady flow of information would connect two distant regions of space. In this sense, Betelgeuse becomes part of a network rather than a destination. But here is something even stranger. If we truly master information, perhaps we do not need to travel at all. Perhaps we can reconstruct Betelgeuse from the data it sends us. Every photon carries information. If we collect enough photons, analyze enough spectra, observe enough variability, we could build a digital twin of the star. A complete high-fidelity simulation, a star recreated in computational space. Inside that simulation, we could travel to Betelgeuse instantly, explore its surface, descend into its convective layers, watch its core collapse from the inside, all without crossing a single light year. This is not travel in the traditional sense. It is experiential reach. And perhaps for advanced civilizations, that is enough. Why risk thousands of years of travel if you can simulate reality with near-perfect accuracy? Why build generation ships when you can build computational universes? This line of thinking suggests something profound. Physical interstellar travel may be rare, not because it is impossible, but because it becomes unnecessary. Civilizations may choose inward expansion, increasing computational power, increasing simulation fidelity, rather than outward migration. The galaxy might be quiet not because it is empty, but because advanced species turn inward into vast digital realities rather than spreading physically. Betelgeuse might already be explored, not by spacecraft, but by superintelligences reconstructing it from afar. Now consider this final twist. We ourselves are observing Betelgeuse as it was 640 years ago. We are always seeing the past. Even if we traveled there physically, we would arrive in the present moment of that star. But Earth would be 640 years older by the time our arrival signal returned. In other words, interstellar travel creates temporal separation that cannot be bridged. Presence at Betelgeuse means absence from Earth's current time. There is no way around this. So perhaps the ultimate barrier is not propulsion. It is simultaneity. The universe enforces delay. It forces civilizations to accept that vast distances imply vast time differences. Maybe reaching Betelgeuse physically is less meaningful than synchronizing knowledge across centuries. Because by the time we arrive, Earth may no longer recognize the civilization that launched the mission. So what does it mean to reach a star? Is it to stand near it, to observe it, to understand it, to simulate it, to send descendants, to send machines? Perhaps the definition itself is evolving. In the next part, we will examine something even more unsettling, because the deeper we look at the scale of interstellar space, the more we begin to suspect that Betelgeuse is not just far. It is part of a structure so vast that even our imagination struggles to hold it. And understanding that structure may change the question entirely. To truly understand what it would take to reach Betelgeuse, we had to zoom out even further, because 640 light-years feels enormous, but only when measured from our human perspective. In the structure of the Milky Way, Betelgeuse is practically next door. The Milky Way galaxy is about 100,000 light-years across. Our Sun orbits roughly 26,000 light-years from the galactic center. Betelgeuse lies in the Orion arm, the same spiral arm as our solar system. On a galactic map, the distance between us and Betelgeuse is barely a small line segment. And yet, that small segment contains 640 years of light travel. This reveals something fundamental about the universe. Space is not just big, It is staggeringly, incomprehensibly vast. Let's put this in perspective. If you could travel at the speed of light, you could circle Earth about 7.5 times in 1 second. You could reach the Moon in about 1.3 seconds. You could reach the Sun in 8 minutes. You could reach Jupiter in 43 minutes. But to reach Betelgeuse, 640 years, and to cross the galaxy at light speed, 100,000 years, and to cross the observable universe, 46 billion light years. Even light, the fastest thing in existence, struggles to traverse the cosmos. This suggests something extraordinary. The universe is structured in such a way that local interactions are easy, but large-scale interactions are slow. Planets interact with their stars easily. Stars interact with their local neighborhoods slowly. Galaxies interact over millions of years. Everything is layered by timescale. Betelgeuse exists in a region shaped by ancient stellar processes. It was born millions of years ago from molecular clouds. It has burned through hydrogen in its core. It now fuses heavier elements. Soon, cosmically speaking, it will collapse. Its lifetime is measured in millions of years. Human civilization is measured in thousands. Our technological age is measured in decades. We are trying to bridge a gap between decades and millions. This mismatch is what makes Betelgeuse feel unreachable. Not just distance, timescale. Now imagine humanity successfully reaching 10% of light speed. At that speed, 640 light years becomes 6,400 years. Still daunting. But something interesting happens at relativistic speeds. Length contraction. From the perspective of the traveling ship, distances themselves shrink. At 99% light speed, the distance to Betelgeuse would appear much shorter from the ship's frame of reference. Space itself compresses along the direction of motion. This is not science fiction. It is a direct consequence of special relativity. So for a ship traveling near light speed, Betelgeuse might feel only dozens of light years away, or less. The faster you go, the shorter the distance appears. But from Earth's perspective, the full 640 light years remain. This dual reality reveals something unsettling. There is no single universal timeline. Travel near light speed fractures agreement about duration and distance. Observers on Earth and travelers on board will disagree about how long the journey takes and how far it is. Both are correct. This is not philosophical. It is physical. So when we ask how long it would take to reach Betelgeuse, we must specify. From whose perspective? Earth's or the travelers? Now consider something even deeper. Betelgeuse is not stationary relative to the Sun. It moves through the galaxy. Stars orbit the galactic center at hundreds of kilometers per second. Over 6,400 years, Betelgeuse will shift position significantly. A spacecraft must account for stellar motion, decades, centuries, millennia ahead. But we can predict stellar orbits with reasonable precision. So navigation is not impossible. It simply demands extremely accurate modeling. But here is a more sobering thought. The galaxy itself is dynamic. Spiral arms shift. Stars interact gravitationally. Molecular clouds collapse and dissipate. On million-year timescales, entire regions transform. On billion-year timescales, galaxies merge. The Milky Way will collide with Andromeda in about 4.5 billion years. Betelgeuse itself will not survive that long. It will explode long before. But this highlights something fundamental. The cosmos is not static. Any journey measured in thousands of years occurs within a moving, evolving framework. You are navigating not just distance, but change. Now let's imagine something radical. If humanity becomes capable of relativistic travel, Betelgeuse would not be unique. Hundreds of stars lie within 640 light-years, thousands, millions within a few thousand light-years. The local galactic neighborhood contains countless red giants, white dwarfs, binary systems, and planetary systems. Betelgeuse is dramatic, but it is not singular. So perhaps the question is not whether we can reach Betelgeuse, but whether we can reach any star beyond our immediate neighbors. If we can cross 640 light-years, then 1,000 becomes possible. 5,000 becomes possible, and eventually the galaxy itself becomes accessible, but only at speeds approaching light speed. And that brings us back to energy. The Milky Way contains about 100 billion stars. If a civilization spreads at 10% light speed, it could colonize the entire galaxy in about 1 million years. That sounds enormous, but in cosmic terms, 1 million years is brief. Dinosaurs ruled Earth for 160 million years. Modern humans have existed for about 300,000 years. 1 million years is not infinite. If interstellar colonization were common, we might expect to see evidence. This is known as the Fermi paradox. If the galaxy is old and large, and if intelligent life arises elsewhere, why do we not see signs of it? One possible answer is that interstellar travel is simply too difficult. Even Betelgeuse at 640 light-years may be prohibitively expensive. Another possibility is that civilizations destroy themselves before reaching that stage, or they choose not to expand physically, or they turn inward into digital worlds, or they use methods we cannot yet detect. But Betelgeuse serves as a concrete test case. If we cannot realistically imagine reaching a star 640 light-years away, then galactic colonization remains hypothetical. And yet, physics does not forbid it. It only demands extraordinary energy and patience. Which brings us to an unsettling realization. The barrier to reaching Betelgeuse may not be physical at all. It may be sociological. Humanity's greatest challenges, historically, have not been physics. Takes fragile trust. Interstellar travel takes fragile trust. Interstellar travel requires trust across millennia. That may be harder than building fusion engines. So perhaps Betelgeuse is not a destination. It is a mirror. It reflects our current limitations, our impatience, our fragmentation, our short-term thinking. To reach it, we must evolve not only technologically, but culturally. And that evolution may take longer than the engineering itself. In the next part, we will confront something even more disorienting. Because when you stretch the question far enough, when you truly grasp the scale of 640 light-years, you begin to see that the real obstacle may not be distance or time. It may be the nature of reality itself. At this point, something unsettling begins to emerge. The problem of reaching Betelgeuse is no longer just about engines, biology, or even society. It becomes something deeper, something structural. Because the more we examine interstellar distance, the more we realize that the universe may not simply be large. It may be designed, at least mathematically, to prevent easy traversal. The speed of light is not just a number. It is a boundary condition. It defines Causality. It defines how fast information can travel. It defines the maximum speed at which influence can propagate. Without this limit, the universe would behave very differently. Cause and effect could reverse. Events could interfere with their own origins. Time itself could lose consistency. So the speed of light is not an inconvenience. It is a stabilizer, a cosmic safeguard, which means that the barrier to Betelgeuse is built into the geometry of space-time. Now consider this. Space is not just empty distance. It is expanding. The universe itself has been expanding since the Big Bang. On cosmological scales, galaxies are moving away from one another as space stretches. At extreme distances, expansion can even cause regions to recede faster than light. Not because they are moving through space at that speed, but because space itself is expanding. Betelgeuse is within our galaxy, so expansion does not meaningfully affect our journey there. But this principle reveals something profound. The universe allows local travel, but it resists universal shortcuts. You cannot simply step across it. You must endure it. Now let's think about causality. If you leave Earth today and travel to Betelgeuse at 99.9% light speed, you may experience only a few decades on board. But from Earth's perspective, 640 years will pass. When you arrive, you are no longer synchronized with your origin. You have leapt forward in time. Interstellar travel becomes time travel. One way. You cannot return to your original era. If you turn around and come back at the same speed, another 640 years will pass on Earth. Your home planet would be 1,280 years older, perhaps unrecognizable. This introduces a deeply personal consequence. Reaching Betelgeuse means severing continuity with your origin. Not metaphorically, physically. You leave your timeline behind. And this is not just philosophical. It affects planning. A civilization launching such a mission must accept that its descendants, not its contemporaries, will see the outcome, which raises a profound possibility. Maybe advanced civilizations rarely attempt such journeys because they fracture cultural continuity. Perhaps civilizations prefer staying synchronized with themselves rather than splitting across centuries. But let's push further. Some theoretical physics suggests that space-time may not be perfectly smooth at quantum scales. There are hypotheses about quantum foam, microscopic fluctuations in the fabric of reality. At relativistic speeds over hundreds of years, even tiny fluctuations could accumulate into unpredictable effects. We do not yet know. We have never sent anything anywhere close to relativistic speeds for long durations. Our fastest probes move at a tiny fraction of light speed, so we are extrapolating. Now consider another radical thought. What if the limitation is not energy, not biology, not engineering, but entropy? The second law of thermodynamics states that entropy increases over time. Systems move toward disorder. A spacecraft operating for thousands of years must fight entropy constantly. Every mechanical system degrades. Every material fatigues. Every radiation impact causes microscopic damage. To sustain order over millennia requires continuous energy and self-repair. This is not trivial. Even Earth struggles to maintain complex systems without maintenance, and Earth has an entire biosphere supporting it. A spacecraft must become a self-sustaining entropy-fighting machine, which is possible in theory, but extraordinarily complex in practice. Now let's confront something even stranger. If Betelgeuse explodes while a spacecraft is en route, the travelers will see something no human has ever seen before. The exact moment of core collapse, the shockwave racing outward, neutrino floods, gamma-ray bursts, expanding stellar debris. From Earth, we would see the explosion 640 years later, but the travelers would see it in real time. In effect, they would become witnesses to the present moment of a distant star, which Earth can only experience centuries later. They would occupy a unique temporal position in the galaxy. This creates a split in knowledge. The travelers know something that Earth does not and will not for centuries. Information itself becomes temporally fragmented. Now imagine thousands of such missions across the galaxy, civilizations scattered in time as much as in space. No unified galactic present, only overlapping asynchronous moments. Perhaps this is the true nature of advanced civilizations, not empires spanning stars simultaneously, but networks of temporal islands, each at different stages, separated not only by light years, but by centuries of delay. Betelgeuse illustrates this vividly. Right now, as you read this, the star we see is from the late 1300s. What it is doing right now is unknowable to us. It may be stable, it may be dimming, it may have exploded. We do not know, which means that, in a sense, Betelgeuse already exists in multiple states, depending on where you observe it from. This is not science fiction, it is relativity. So perhaps the final barrier is epistemological. We can never access the universal now. Every observation is delayed. Every interaction is bound by light speed. Even if we reach Betelgeuse physically, we are simply updating our local frame. The universe remains fundamentally partitioned by time, which suggests something extraordinary. Maybe the universe is not meant to be traversed quickly. Maybe intelligence evolves locally, explores locally, and only slowly extends outward. Perhaps the speed of light limit acts as a cosmic pacing mechanism, preventing rapid homogenization, ensuring diversity across space. If faster than light travel were easy, the galaxy might already be unified. Instead, it remains quiet, separated, vast. So when we ask how long it would take to reach Betelgeuse, we are really asking, can we overcome the pacing of the cosmos? Can we match our ambition to its scale? Or are we confined, at least for now, to watching from afar? In the next part, we will approach the question from one final direction. Because after all the physics, biology, engineering, and philosophy, there remains a single stark number, 640. And that number may tell us everything. 640 is just a number. But when attached to the words light years away, it becomes something almost abstract. Betelgeuse is approximately 640 light years from Earth. That means if you could travel at the speed of light, the absolute cosmic limit, it would still take 640 years to arrive. And since nothing with mass can reach light speed, the true number is always higher. So let's strip away speculation for a moment. No warp drives, no wormholes, no exotic matter, just physics as we understand it. If we build the most advanced propulsion system realistically conceivable within known science, something capable of 10% the speed of light, the journey takes 6,400 years. At 20% light speed, it takes 3,200 years. At 50%, 1,280 years. At 99%, 640 years from Earth's perspective, though far less for the crew due to time dilation. Those are the hard numbers. Now compare that to human history. The Great Pyramid of Giza was built about 4,500 years ago. The Roman Empire fell roughly 1,500 years ago. The printing press is only 600 years old. Modern electricity, about 150 years. The internet, roughly 40. Civilizations shift dramatically in centuries. Languages evolve beyond recognition. Entire belief systems transform. A 6,400-year mission is longer than recorded human history. A 1,280-year mission is longer than most continuous political systems have ever survived. Even 640 years, the absolute minimum under relativistic travel, is longer than most nations have existed. This forces a simple but brutal conclusion. Reaching Betelgeuse is not about building a ship, it's about building continuity. And continuity at that scale may be humanity's greatest weakness. We are brilliant in bursts, revolutionary in decades, but stable across millennia? That remains unproven. Now imagine we do it anyway. A relativistic ship departs Earth at 99% the speed of light. From Earth's perspective, 640 years pass before arrival. By then, Earth may have transformed into a machine civilization, colonized dozens of nearby stars, collapsed into ecological ruin, or vanished entirely. The travelers arrive at Betelgeuse not as ambassadors of their time, but as relics of an ancient Earth. They left one civilization. They arrive representing a fossilized version of it. Because while they experienced decades, Earth experienced centuries. They are temporally displaced. Time dilation ensures they never truly return to the moment they left. And that is the unavoidable cost of relativistic travel. You trade spatial distance for temporal separation. Now let's confront another stark truth. Even if we achieve 99% light speed, Betelgeuse may no longer exist in its current form. Red supergiants like Betelgeuse have lifespans measured in millions of years, but their final stages are volatile. It could explode tomorrow. It could explode in 100,000 years. If it explodes 100 years after we launch, Earth will see the supernova 740 years after departure. The travelers, however, may arrive to find a neutron star and expanding debris. The star they aimed for would be gone. This unpredictability makes Betelgeuse a moving target in time as much as space. And then there's deceleration. Reaching near light speed is only half the problem. You must slow down. Otherwise, you simply fly past your destination in seconds, which means doubling the energy requirements. And shielding. At relativistic speeds, interstellar hydrogen atoms strike like bullets. Dust grains become micro-explosions. The ship must endure a constant barrage for years. Even a tiny flaw could be catastrophic. So let's reduce everything to its essence. To reach Betelgeuse physically requires energy on the scale of planetary output, engineering capable of surviving centuries, shielding against relativistic hazards, autonomous systems that function flawlessly for decades or millennia, acceptance of temporal dislocation. A civilization willing to invest in a project it will never personally see completed. That's the reality. Now here's the twist. Even if we never reach Betelgeuse physically, We are already connected to it. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in ancient supernovae, stars like Betelgeuse. In a cosmic sense, we are already descendants of red supergiants. We do not need to reach Betelgeuse to be connected to it. We are made of its kind, which reframes the question entirely. Perhaps the urge to reach Betelgeuse is not about conquest or colonization. Perhaps it is about curiosity, about witnessing a stellar death firsthand, about standing near a star in its final moments and seeing the processes that created the elements of life. But if that witnessing requires 6,000 years, if it demands energy beyond planetary scales, if it fractures civilizations across centuries, then maybe the better question is not, how long would it take to reach Betelgeuse? But what kind of species would be required to do it? Because that species may not look like us. It may not think like us. It may not live on planets at all. It may be post-biological, post-scarcity, post-impatient. Betelgeuse may not be unreachable because it is too far. It may be unreachable because we are too early, too young, too newly technological. Humanity has had spaceflight for less than a century. We have had radio astronomy for less than one. Fusion power is still experimental. Relativistic propulsion remains theoretical. In cosmic timescales, we are infants asking whether we can cross oceans of light. Perhaps the answer is not never. Perhaps the answer is not yet. In the final part, we will bring everything together, because once you truly understand what 640 light years means, physically, temporally, philosophically, the question transforms from a calculation into something much larger. It becomes a statement about our future and whether we are destined to remain beneath our single star or someday cross the darkness between them. When we first asked the question, how long would it take to reach Betelgeuse? It sounded like a calculation, a matter of speed divided by distance, a simple equation. But now, after everything we have explored, the number no longer feels simple. 640 light years, 6 quadrillion kilometers, 1 million years at current spacecraft speeds, thousands of years even with propulsion far beyond today's technology, centuries at near-light speed. And with every improvement in speed, we discovered something deeper. The faster we go, the more time fractures. The closer we get to light speed, the more the journey becomes temporal exile. You can shorten the trip for the crew, but you cannot shorten it for Earth. Relativity does not eliminate distance, it reshapes it, and in doing so, it forces a choice. If we ever reach Betelgeuse physically, we will not arrive as representatives of the present. We will arrive as echoes of the past. Because while the travelers experience decades, centuries will pass on Earth. The world they left will be gone, replaced, transformed, or forgotten. And perhaps that is the true cost of interstellar travel. Not energy, not shielding, not engineering, but continuity. To reach Betelgeuse is to accept that you will never return to your own time. Now consider Betelgeuse itself. Right now, as you sit beneath the night sky, the light you see left that star around the year 1385, before the printing press, before modern science, before telescopes. The Betelgeuse of now is hidden from us. It may already have exploded. It may still be swelling and shedding mass. It may be in its final centuries. We simply do not know, because information itself travels at light speed, and that is the ultimate barrier. No matter how powerful we become, we cannot escape the fact that knowledge is delayed by distance. Even if we could teleport instantly, which physics does not currently allow, information about Earth would still take 640 years to reach Betelgeuse, and information from Betelgeuse would take 640 years to reach Earth. The universe enforces delay. It enforces separation. It ensures that stars remain islands, which makes Betelgeuse not just distant in space, but distant in time. And this is where the question transforms, because maybe the real journey is not to Betelgeuse. Maybe it is to maturity. Human civilization has existed for perhaps 10,000 years. We have had electricity for about 150, spaceflight for about 70. We are standing at the shoreline of the cosmos, asking if we can cross an ocean 640 light years wide. Perhaps we are too early. Perhaps interstellar travel requires centuries more of energy development, material science, artificial intelligence, and social stability. Perhaps it requires becoming a Type 2 civilization, harnessing a significant fraction of the sun's power. Perhaps it requires redefining humanity itself, biological longevity extended, digital consciousness, autonomous machine explorers. Because a journey to Betelgeuse is not a mission, it is a transformation. The civilization that launches it will not be the civilization that arrives. Now let's return to the raw numbers. At current technology, over 1 million years. At optimistic fusion speeds, thousands of years. At 50% light speed, 1,280 years. At 99% light speed, 640 years from Earth's perspective. There is no scenario within known physics where Betelgeuse becomes a short trip. There is no version of reality where it becomes casual. It remains vast, and that vastness may be the point. The universe is structured in layers. Planets are reachable in months or years. Nearby stars in decades or centuries, perhaps. Distant stars in millennia. And galaxies in tens of thousands of years. The cosmos scales its distances in proportion to time. It forces patience. It forces perspective, which leads to one final realization. Maybe the purpose of asking how long it would take to reach Betelgeuse is not to plan the journey. Maybe it is to understand our place. Betelgeuse reminds us that the night sky is not a backdrop, it is depth. When you look at Orion and see that red star, you are looking across 640 years of history. The photons entering your eyes began their journey before the Renaissance. They crossed unimaginable darkness to arrive at your retina. And in that moment, you are connected to a star that may already be gone. That connection is real. It does not require engines. It does not require fusion reactors. It does not require antimatter. It requires awareness. We are already participants in the cosmic story. The elements of our bodies were forged in stars like Betelgeuse. The light of distant stars shapes our understanding of physics. Our telescopes decode their atmospheres. Our detectors capture their neutrinos. In a sense, we have already reached Betelgeuse. We just have not touched it. And maybe touching it is not the ultimate goal. Because to reach Betelgeuse physically would demand energy, patience, and unity at a scale humanity has never demonstrated. It would demand thinking in millennia. It would demand building for futures we will never see. And perhaps that is the real test. Not whether our engines can accelerate fast enough, but whether our civilization can endure long enough. Because if we ever do stand near Betelgeuse, watching its surface convulse, waiting for its core to collapse, that moment will not just represent technological triumph. It will represent something far greater, proof that a species born on a small blue planet beneath a single star learned to think in cosmic time. Until then, Betelgeuse remains what it has always been, a distant, glowing reminder of how vast the universe truly is, 640 light-years away, and, for now, beyond our reach.